Welcome to this long-running series, 14 years. I think that in Livermore, science is in our blood. Who would have thought 1,000 people would come out on a Saturday morning to hear scientists talk about their work and about their passion? We at the schools are grateful to the lab for providing the opportunity for all of us to learn what's going on right under our noses at the far end of East Avenue. As I noted last week, we're deep into the science fair season. There was Livermore's Science Odyssey last week. How many had projects in that Odyssey? See a few hands. This week is the Tri-Valley Science and Engineering Fair, sponsored by the lab. Students from all Valley schools may participate and win prizes. Our fair is affiliated with the Intel International Science and Engineering Fair. Our winners advance to higher levels of competition. Athletes have games, musicians have concerts, but science students have science fairs, and the rewards are just as great. The winners of the Intel Fair can win a $50,000 scholarship. Last year, a Tri-Valley winner at our show walked away with an $120,000 tuition scholarship, along with several other awards, including a paid summer internship. I hope you'll visit the fair. It's at the Robert Livermore Community Center, Thursday evening, March 6th. Today our topic is greenhouse gases. Julio Friedman is our presenter. He has degrees from MIT and a PhD from USC. He worked as a senior research scientist at ExxonMobil and later worked as a research scientist at the University of Maryland, affiliated with the Joint Global Change Research Institute. I wonder how you string those letters together to make it sound like something. And the Colorado Energy Research Institute at the Colorado School of Mines, before joining Lawrence Lab as a carbon management program leader. They say join the Navy and see the world. Julio has seen the world in his pursuit of carbon. Spain, Ireland, the North Sea, Nigeria, Angola, Venezuela, Azerbaijan, and Australia. Who says scientists stay at home in their labs? Brett States, the co-presenter, has taught middle school and high school science in Tracy for 10 years, and he'll be sharing the duties today. He's a staff developer for the K-12 Alliance and coordinates science for Science and Technology Magnet School in Tracy. John Ziagos is another contributor. He's a senior scientist at the lab, responsible for achieving a vigorous energy and environmental research portfolio through the technical and business leadership of 200 scientists, engineers, technicians, and administrative staff. He has a PhD in geophysics. And now, greenhouse gas reduction, underground storage of carbon dioxide.
Thank you very much for that, Anne. Thanks to the lab, the Bankhead Theater, and especially thanks to all of you. It's getting very nice outside, and I'm just astonished that we can get 400, 500 people in here to learn about climate change and to learn about what can be done about it. So kudos to you all. We're going to be talking here about greenhouse gas emissions and what that might mean, and we're going to talk about things that can be done to reduce our emissions and to manage that problem. But there's a number of things that we're going to get out of this talk, and there's some people here who are here formally, and in that context I want to make sure that everybody's clear on what the end goals of today are. So one of them is you're going to learn a bit about what causes climate change. And in this we're not talking about the long-term natural variations in climate change, but what's driving our current climate change in terms of man-made emissions. You're going to learn that CO2 in the atmosphere has gotten in there faster than we thought. The situation's much more dire and much more severe than most people understand. Burning of fossil fuels is the primary source of man-made CO2 in the atmosphere. About 85% of that, we'll be talking a bit about that. I'm going to spend a lot of time talking about one of the things that can be done. And there are many things that can be done to manage this problem, but one of them is carbon capture and sequestration. That's one that most people don't know about, as opposed to, say, wind power or solar powers. And so we're going to spend some time talking about that, and specifically also what Livermore is doing in that arena to help things along. Now, before we get deep into the talk, we're going to try to get a sense for what people here know. Because I've talked to people in bus stations and trains and wherever I go, and I try to engage them in conversation and go, what do you know about climate change? And most people go, not much. And so it's worth trying to get a sense of what you understand early on. And in order to do that, we've actually got a number of contestants here on stage, and we're going to be playing a quiz show to get them, to see if what they know. And these are, of course, the finest of the Tri-Valley area. And we're going to be having a number of other questions which you guys can all track your own brains against. So with that, I'm going to turn this over to Brett.
All right. We're going to call our game show Carbon Quiz. Game shows are very popular now. We debated whether we do lifelines or not, but we'll see how that plays out. I'd like to introduce our first participant. Your name, school, and where you're from, please.
I'm Rebecca Harris. I'm from Livermore Valley Charter School.
And what grade?
Oh, 7th.
Thank you. Let's give Rebecca a nice warm welcome. Contestant number 2. Introduce yourself, grade, and where you're from.
Me llama Clarissa.
Ooh, español. Muy bien.
The school is Livermore Valley Charter.
Okay. And what grade?
7th.
7th grade as well. Let's welcome Clarissa. Contestant number 3.
My name is Heath Vaishnav, and I'm in 8th grade in Stone Valley Middle School.
And where's Stone Valley Middle School?
It's in Alamo.
Alamo, California. Welcome, Heath. All right. Very good. So, 2 7th graders and an 8th grader. Let's get right to it, shall we? Carbon quiz. Question number 1. What is the cheapest method of making electricity? What is the cheapest method of making electricity? No help from the audience, please. All right. Oh, we have a clean sweep of letter D. All 3 like letter D. All right. And the correct answer for question number 1, what is the cheapest method of making electricity? It is actually coal. That's okay. That's okay.
Actually, that's important to know. If it was actually cheaper to make electricity with wind, then we wouldn't be having this problem, because wind doesn't make carbon dioxide.
In all fairness, they spend a lot of time up and over the Altamont, so they see it, right?
Right.
Right, okay. Question number 2. Zeros across the board. Let's get someone on the board this one. Number 2 is, how much carbon dioxide do humans put into the atmosphere each year? In billions of tons, how much carbon dioxide? We have an upside down B. That's okay. That's okay. All across the board, A, B, and C. All right, no changing your mind now. There we go, and the correct answer is letter B. Score 10 for Rebecca. 31 billion tons.
I'm going to take a second here with respect to the next question, which is, most people don't know what 1 billion tons really means. You don't go to the store and buy, 1 billion tons of carrots. So there's some scale in which it needs to get that into your brain. So that's what this next question is for.
All right, with that, number 3. What is the approximate combined weight of every person on Earth? Interesting question. Combined approximate weight of every person on Earth. A, 1 billion tons. B, 32 billion tons. C, 10 billion tons. Or D, none of the above. Good test-taking strategy. Every student should know that if you ever see none of the above, your chances are pretty good that that's correct. And in this case, it holds true. It is correct. None of the above. The correct answer is actually 1/2 of a billion.
Right. So there's about 6 billion people on Earth. For it to be 1 billion tons, everybody on Earth would have to weigh about 350 pounds. So not even in California is it quite like that yet. So it's a lot closer to about 1/2 billion tons.
All right, with 2 questions to go. Rebecca's in the lead with 20, and then 10 and 10 for a tie for second. Question number 4. Which fossil fuel is the single largest contributor to carbon dioxide in the atmosphere? Is it A, natural gas, B, coal, or C, oil? What's the single largest contributor to carbon dioxide in our atmosphere? Clean sweep of B. Audience, let's poll the audience. Shall we give them a lifeline? How many people think it's letter A? Raise your hand for letter A. A couple of you. How about letter B? You gonna go with our contestants? You think they're right? Anybody for C, for oil? Oh, okay. The audience and the contestants are correct. It is coal. Mr. Farnsworth updates the scores. That leads us to 30, 20, and 20. Close race here. It's going to come down to the final question.
Wait, before that. On this, basically, coal has about twice the carbon dioxide of oil, and oil has about twice the carbon dioxide of natural gas. Coal is also the primary source of electricity around the world, so coal puts about 25% of that 31 billion tons into the atmosphere. It's the single biggest thing we do.
All right, we're either going to have a clear-cut winner or a three-way tie here on this one. Let's see how it works out. Question number 5. How much carbon in pounds is produced by an automobile when it burns a single gallon of gasoline? Is it A, 1/2 pound, B, 1 pound, or C, 5 pounds? They're all going with the same. A last-second change. Lock them in. Lock in those answers, shall we? Is that your final answer? Audience, who's right? C, it is 5 pounds. With that, we have a winner. And it is Carissa with, we tied. We tied, but that's okay. We have prizes for all of them. Let's give them a round of applause here, shall we? Guys can go ahead and stand up. We tied, but everyone gets prizes. All right, we get prizes. The coveted Science on Saturday Slinky.
No, I like my Slinky.
That, you guys want to take your seats?
Yes.
All right.
I don't. Okay.
Thank you very much. All right, with that last answer, kind of give you a visual about that. 5 pounds. This is as close as I could get. It's not actually 5 pounds. It's a little more. But there's 100 of these in here. So think about that. 5 pounds of carbon.
Right. So another way to think about that is the average efficiency of a car in the United States gets about 25 miles a gallon. There's about 5 pounds of carbon in a gallon of gas. At that kind of a rate, if you get 25 miles a gallon at 5 pounds a gallon, you put a briquette out of your window every quarter mile. That's a lot of carbon. Imagine what the freeways would look like if you actually threw a briquette out your window every quarter miles. It's a lot of carbon dioxide. And in this context, it's important to understand how difficult the problem this is. And with that, we're going to go back to the computer. This is not the sort of thing that you fix by telling Dow Chemicals to change their refrigerants. It's a different class of problem. Everything that people do, more or less, puts carbon dioxide into the atmosphere. And in that regard, it's not, you have to sort of make vast changes to our energy infrastructure, to our way of life. You have to do something big in order to get a big response. So if we can get back to the computer here, I've tried to express this in a way that most people don't see. The graph that you're looking at here is actually all of the energy used since the Industrial Revolution. And what you can see is a couple of things. One, it goes up a lot. It doesn't ever really go down. It goes up a lot, and it keeps going up fast. And it continues to go up quickly into the current age. And all projections for energy demand go up. There isn't one that actually goes down in any scenario that people talk about. The other thing you'll notice about this is we've never used less of any kind of energy ever. We use more wood than we used to use. We use more coal, we use more oil, we use more gas, we use more nuclear. We never use less of anything. And the thickness of the top line is the thickness of current renewable portfolio. So now 85% of that at the end of the line there is fossil fuels. Now if we used, from today forward, if we said all new energy demand is going to be met through conservation and through renewable supplies, that'd be A, impossible. It'd be really hard to do. But B, even if we did it, we'd still be venting 31 billion tons of carbon dioxide because we don't use less. And there's a good reason for this. Fossil fuels are awesome. They're cheap, they're abundant, they're distributed broadly across the world, they're stable. That coal isn't going to blow up when you look at it. It just sits there. And if you think about the energy density of fossil fuels, there's a lot of energy in that gallon of gasoline. Another way to put it, my car gets about 30 miles to the gallon. I'll tell you what, gas is $4 a gallon now. I'll give you $4 to push my car 30 miles. you know, which is why actually if gas is $5 a gallon, $8 a gallon, like it is in Europe, or $10 a gallon, like it is in Japan, people don't change what they do. They still drive cars because it's a great bargain. And that's the challenge, is that you actually have to offset something that's so good. The problem, though, is despite the fact that fossil fuels are so great, they emit carbon dioxide, and that's a problem. The blue chart is basically increasing global mean temperature. And again, sort of thing where you see there's this long-term sort of trend. There's some small oscillations in it, but really it goes up and it stays up. And there's no scenario we see in which that changes. We see that global average sea level and also global average sea temperature goes up. Most of the sea level is just due to the thermal expansion of the water. The water gets hotter, it swells. That causes sea level rise. You also see the northern hemispheric snow cover has been decreasing. That's bad for us in California because a lot of our water comes from the snowpack, and if we have less snow cover, we have less water. So how do we actually know, though, that this is caused by people? And this is a reasonably good question to ask. And I'll say right now, if you asked us that question about 15 years ago, we didn't have a good answer. We had some good ideas, but we didn't have a good answer. Now we've got a pretty good answer. So the black line shows us what the actual temperature changes have been. Okay, so that's the real record. Blue is when we take our ensemble of climate models and we say we're going to run this, but without increases of carbon dioxide. We're going to take changes from volcanoes, changes in solar luminosity. We're going to dial all that into our climate models, and off we go. And what you see is it does pretty well for a while, but after about the 50s and 60s, you just can't make today's climate that way. You just can't. And actually, we do a lot of that at Livermore. Most people don't know this. Livermore has a huge climate program. We run all of the world's climate models, all 25 of them, and we compare them and diagnose them and watch them get better. However, if you take those climate models and you throw the CO2 into it, which we know from combustion and utilization of fossil energy, then you get the red line. And if you'll see, the red line and the black line are a pretty good match. And so it's entirely credible now that we understand this. And the Intergovernmental Panel on Climate Change basically came to that consensus between 120 nations this year, in which they said, we know it's 90% likely that human beings have caused this, that the changes are real, and that it's bad, and that it's going to get worse. I don't know if you've ever tried to get consensus from 120 people, but 120 nations is pretty hard. And so this is actually really quite serious. And most people, again, don't get how bad it is and what this means, so I'm going to try to illustrate it. In order to understand what kind of world we want to live in, the IPCC uses scenarios. And these different colors here represent different scenarios, and each of the scenarios is one kind of world we could live in. The orange line is the business as usual scenario. Most people don't realize the business as usual scenario has in it a 1.4% annual efficiency improvement worldwide, also a doubling of nuclear and a quadrupling of solar power built into it. That's the business as usual scenario. Okay. Now the worst case scenario is the red one. The red one says rapid population growth, rapid economic growth, low technology focus. The red dot is where we are. We are already well above the worst case emissions scenario that the IPCC used. We put 31 billion tons of carbon dioxide into the air every year. That's about 60 or 70 times the mass of all the human beings every year. You don't fix this with compact fluorescent light bulbs. You've got to do something more. And we know that it's bad, and one way of knowing that it's bad has actually been to look at the changes in the ice sheets. And in this case, I'm going to focus on the polar ice cap. And you saw in the news back in 2007, suddenly everyone was talking about the polar ice cap. We didn't exactly know why we would be talking about it all of a sudden. This is why. We've been tracking it for a while. Since about the mid-'70s, we've got satellite data that shows what's going on. Now, suddenly, it just starts going away. And this is only to 2005. In 2007, over 2 years, it's dropped 30% from this. Over the course of those 30 years, we actually lost about 60% of the volume of the ice because it's gotten thinner, too. And that's bad news because white reflects light back into space. So that the ice here actually helps keep the Earth cooler. When you replace that with ocean, the ocean absorbs it, and actually it's a positive feedback. It warms up the atmosphere. So that's not so good. It turns out that ensemble of climate models I was talking about, if you run the worst case emission scenario, that red line from the IPCC, this doesn't happen for another 20 years. This happens in about 2027. It's actually already we're seeing much more dire consequences than we can predict with our models, which means that the situation's worse than we thought. And we've also seen that the global temperature is changing more rapidly over time. So the blue line is, again, the temperature record. The red line is sort of a 100-year smoothing trend, the 50-year smoothing trend, and actually the 10-year smoothing trend is even faster than that. And the punchline is now we're seeing that, again, the past 15 years have had the 12 warmest years on record. So there's no good news in this. The more that we study it, the worse it looks. So to come to a conclusion, it's real, it's worse than we thought, it's getting worse faster than we thought. So we're unbuckled in the car, we're heading off a cliff, and we've got our foot on the accelerator. That's the setup. Our response is about this cartoon. How about you spend less time studying how my generation destroyed the environment and more time figuring out the magical solution? You know, people like the idea that there's some quick fix or a silver bullet, but there isn't. Part of the good news, though, is we don't actually need a silver bullet. Lead bullets are fine if you have enough of them, and the good news is we have enough of them. But we have to take action, and that action is urgently warranted. So let's put this into some perspective. One of the things you'd like to ask yourself is what matters? What makes a difference on some level? So you can think about the atmosphere as a bathtub, where the shape and the volume of the bathtub is basically constrained by Earth's gravitational field. And that's what keeps the atmosphere in the shape it is. It has about 3,000 billion tons of CO2 in it today. Every year we put in about 30 billion tons, and every year nature takes out about half of that, 15 billion tons. Roughly speaking, it goes split between the ocean and the landmass, which means every year we put 15 billion tons in that stays in. So it goes up quite a bit every year. So if you're going to do something about this, you have to be working at this 15 billion ton a year level that stays in. If you're not hitting at that kind of level, then what you're doing really doesn't substantively matter. Another way to think about the same sort of thing is what do we need to do to do something useful? So here we've got the emissions trajectory up to about 2000, and then we've got the current trajectory, which is this upward ramp. It's more complicated than that, but let's just say it were to go up fast constantly for a while. In order to actually stabilize concentrations, you have to go flat for a while and then go down. If you don't, concentrations keep going up. So that's a trajectory for about 550 parts per million. Now that's already probably too dangerous. We're at 390 parts per million today. We've already got some serious effects. 450 parts per million is also probably too dangerous. So if you actually wanted to really fix this problem, you need actually to go down pretty much right away. But let's say that we're not going to do that. We're going to try to flatline for a while our emissions. That'll be very hard, and then later on we'll go down. So you can think about that in terms of what's called a stabilization triangle. The difference between the current trajectory and a flat line is that amount of CO2, which is a lot of CO2. That means that in 50 years, we need to be putting 30 billion tons a year less in than we're putting in today, than what we would otherwise. Well, okay, well, what can we do to do that? What are things that matter? One of the things you can do is say, we're not going to think about one huge wedge. That's overwhelming. I'm going to break it up into bite-sized chunks. I'm going to make 8 wedges. And the reason why it's 8 is because each of those things is 4 billion tons of CO2 tall in 50 years. And over 50 years, that means it's 100 billion tons of carbon dioxide. So it's a nice round number. It's something we can do. So anything that gets us one wedge, these are called stabilization wedges. Anything that gets you one stabilization wedge is worth talking about. If it doesn't, it's not worth talking about. Tidal power, not worth talking about. It can't get you a wedge. Wind power, worth talking about. Wind power can get you a wedge. And this whole framework for thinking about it was put together by a couple of professors from Princeton, Steve Pacala and Rob Sokolow. And they did this as a way to illustrate to people what we should be doing today to start reducing emissions and what's on the table. And so they came up with about 15 different technologies that could get you one wedge of abatement. And then they told you what it would take to do these things. So let's take, for example, automobile efficiency. Everybody goes, yeah, we want more automobile efficiency. That's a good thing. And it is. So what does that look like? One wedge of automobile efficiency is doubling the efficiency of every car on the planet. That's hard and expensive, but that gets you one wedge. So you need another 7. Let's say you like nuclear power. Nuclear power is good. It doesn't emit carbon dioxide into the atmosphere. Let's say that you like nuclear. Okay, off we go. That's about 400 nuclear power plants, big ones, 1,500 megawatt jobbers. That gets you one wedge. That's a bit more than all the nuclear plants in the world today. You have to get another set of those. Let's say that you like wind power. Wind power is good. Doesn't emit emissions, it's stable, you can do whatever, if you like it, off you go. That's about 2 million windmills, is one wedge of wind power. I think the Altamont has, what, a few hundred windmills? So we're talking about 3 orders of magnitude of scaling up. It's not easy. None of these things are easy, and each of those gives you one and only one wedge. So one of the things that we need to talk about in this context is that you have to fire on all cylinders. You want all options on the table right away. And one of those options is something called carbon capture and sequestration. You guys mostly have probably not heard of that, so I'm going to spend a lot of time talking about that today. Most of you have heard about wind power or solar or nuclear, but you probably haven't heard about this. There's a couple of things that are useful about it. One, it's cheap, comparatively speaking. When you compare it with all the other options, it's cost competitive. 2, it uses proven technology. No miracles required. This is not cellulosic ethanol, which will be ready in 30 years, or space-based solar power. This is something you can do now. 3rd, it applies to new and existing plants. You can go to any power plant, slap on a capture device, and put the CO2 underground. And the last thing is, it's going to get a lot cheaper, because we haven't really had to worry about this at this scale. So the costs that I'm talking about today are the current costs, just like all the other technology options we have. The more of it we do, the cheaper the costs will get and the better it will look. So let's say you have to get the stabilization wedge. What's a good fraction of that? What can you do? And this was an analysis done by some guys in Sweden. And basically, there's a couple of things that come out. The yellow options involve carbon capture and sequestration. The green options are the green options. And the blue options are changing fuels. A couple of things. First of all, the cheapest thing on this list is carbon capture and sequestration. As the first thing you do is you use that to get enhanced oil recovery. You get some oil out of the ground by injecting CO2, which is why we know so much about this. The 2 biggest boxes are carbon capture and sequestration. Combined, you can maybe get 25% of the problem. Most of the green options are more expensive. Important thing to know. Solar is much more expensive. Wind is more expensive. Biofuels are more expensive than those options. Nuclear wasn't in this, so with the red boxes there are nuclear. Nuclear in this case is about 50 to 80 bucks a ton for avoidance, depending on how you calculate those numbers. So nuclear could maybe get you 20% abatement, but its costs are, again, in the same sort of ballpark. So this makes carbon capture and sequestration an attractive option, because if you got to decarbonize the atmosphere, you want to do it in the cheapest way you can. We know we can get at least one wedge this way. And the reason we know that is because the amount of oil that we produce on a volume basis is about equal to the amount of CO2 associated with one wedge. If we can take all of the CO2, all of the oil that we used, or all the natural gas that we used, turn it into carbon dioxide, and then put it back underground, that's about the same volume of stuff. So what you're looking at here is a coal-fired power plant in Indiana. They don't actually burn coal. What they do is they turn it into a gas and then burn that. Now that gas, you could strip the carbon out of it first and not burn it. And that's one way that you can manage the carbon dioxide. The picture on the left there is a picture of what they're doing in Norway today at a platform called Sleipnir. I'm going to talk a bit about that, in which they actually take the CO2 out and re-inject it into a shallow, to a deep saline formation. I'll explain all that stuff. But basically, this is what you'd be doing. You'd be taking the CO2 from a power plant and you'd be injecting it underground. Now, to do this, you need about 800 of these kinds of plants at 1,000 megawatts each. So this is not easy either. I don't want to leave you with the notion that this is some sort of panacea and it all goes away. But it's one of the things you want because of that 31 billion tons we have to manage. Now, this is not rocket science. This is rock science, okay? Basically, what we're saying is we found some place in the crust, we're going to inject a lot of CO2, and it's going to stay there. The vertical scale bar here is about 2 kilometers. So this is not like digging trenches in your backyard and you put a bunch of CO2 in it. Here we're actually talking about a kilometer or a mile of the Earth's crust on top of your injection position. The 2 places you can put it, depleted oil and gas fields. That makes sense, right? You take the oil out, you put the CO2 back in. That's something that most people sort of get inherently. With respect to the saline formations, though, basically wherever there isn't an oil field in the Earth's crust, away from that oil field is the saline formation that's the same rock unit, but just doesn't have oil in it. And so those are also places you can put CO2. Our published estimates for what that looks like on a global basis are about 10,000 billion tons of capacity. So we take our 31 billion tons, we probably got at least 50 years, maybe 100 years of capacity for sure, and possibly hundreds of years of capacity to put CO2. So that's not the limiting factor. The limiting factor is, do we do it? And that's a substantial question. So what happens when you inject it underground? A couple of things. First of all, it's trapped physically, the same way that oil and gas is. CO2 is buoyant in the crust, so it would come back to the surface as it weren't trapped under some rock. So you can say that gray rock over there, this porous and permeable, the overlying rocks, the red rocks, are not. It's trapped underneath that and would be stored indefinitely. There's also something called residual phase trapping. This is basically the same reason you throw your clothes in the dryer. Even after you wring out your clothes, they're still wet. And the reason why is because the little tiny pores in your clothes trap the fluids because of capillary forces. That's why you throw your clothes in the dryer. Same thing happens in the rocks. The little rocks contain little void spaces called pores. And those void spaces also have capillary forces acting on them, and they will also trap CO2 and keep it from moving around. That's basically stuck down there permanently. It doesn't move again once it's down there. Over longer periods of time, the CO2 dissolves into those saline waters, into those brines. And then it basically becomes Perrier. And the good news is that Perrier is more dense than the water around it, so it sinks. It's not buoyant anymore. So again, it's stuck permanently. The only way to get it out is, I'll drink your milkshake sort of thing. You actually have to punch a hole into it and suck it out to get the CO2 back out. Over longer periods of time, and that's what that simulation at the bottom shows, the CO2 actually forms carbonic acid and then reacts with the rocks, and it makes new minerals. Those new minerals, the only way to get them out, the only way to get the CO2 out at that point is plate tectonics. You have to slam South America into Texas to get the CO2 back out. So there's another way to sort of, in thinking about that exact question, and we're going to jump to this one, what we have is we have lots of storage mechanisms that act over different time scales, and over time it gets more and more secure. That's a nice factor of this carbon sequestration. It means that, again, the chance of success is high. Now with that, we're going to have another demonstration here. I'd like to pull Brett back out. He's going to talk about what happens to the CO2. Where does it go actually when you put it underground?
Glass beads, there I am. Hello. Glass beads inside this plastic tube to represent the crust, the layers that Dr. Friedman was talking about, and some Crayola modeling clay as our capstone, our impermeable layer on top. So it's filled with water and glass to represent the crust of the Earth. Instead of using carbon dioxide, we've got a simple mixture of blue food coloring and cooking oil, canola, which, as Dr. Friedman was just sharing with me, has a lot of the similar properties of carbon dioxide, the buoyancy and some other characteristics that are pretty similar. So it's actually a good simulation of what we're talking about when we try to capture and sequester the carbon. So here we go. Let's see what we have here. I insert this into my stop valve, open it up, and hopefully the water doesn't come blasting out at me. Squeeze some of our simulated CO2 into the Earth. And hopefully the camera's picking that up. Dr. Friedman, feel free to give us a play-by-play here, too. What we see.
In the deep crust, the CO2 has about the same density and viscosity as oil does. And so what you're seeing here is it's buoyant. It's floating upwards, which it is. And ultimately, it's going to get caught at the top. And we're going to pan up in a minute, but not right now. But it's going to get caught up at the top, and it'll be trapped underneath that layer. In the meantime, if you stay down at the bottom, you'll notice that some of this stuff is actually getting stuck behind. After the injection is over, it just gets left in these pores. Like there's a little bit that it's not moving anymore. See that right there? That's that residual phase trapping, that capillary trapping. The only way that we can get that out actually is by flushing it with hot water. Otherwise, it's really, really tough to get that CO2 analog out of there. So if you'll stop injecting and we wait over time, now we're going to go towards the top. And you're going to see that some of the CO2 is actually at the top of this going to actually get trapped beneath this plasticine, which is acting like our impermeable cap rock. We're going to go up there, and here it is. It just gets stuck underneath that. And the reason why it's stuck between, there's pores in this clay, but they're so tiny that the oil just can't squeeze through it. And that's basically the same way it works in the Earth's crust. So when we stop injecting, what we see then is some of this stuff just gets stuck behind. It stops moving. Here's some that stop moving. Here's some that stop moving. And it just gets trapped there. So you have multiple trapping mechanisms, the physical trapping of this cap rock, and ultimately the interstitial or the capillary trapping of the rest of the volume. So a reasonable question to ask yourself now is, so how do we do this? What's to be done? Step one, choose a good site. If you don't have a good site, things can go wrong. So put some effort up front, do the work, and make sure that it works. And in order to have that, you need three things. You need injectivity. That's the rate term, how fast can you put it underground. You need capacity. That's the bulk term, how much CO2 can you hold. And you need effectiveness. It has to stay stored effectively over long periods. ICE, or ICE, is one way to remember this. So let's take the injectivity. A single 1,000 megawatt coal-fired plant puts out 6 million tons of CO2 a year. That means any site you choose has to be able to receive 6 million tons of CO2 a year. If it can't, it's not a good site. The bulk term, the volume term, if you run that project over 60 years, you have to choose a site that can hold 360 million tons of carbon dioxide. That's a lot. To give you a sense of a lot, in the terms of volume terms, at these pressures and depths, that's about 3 to 4 billion barrels of oil. It's the same volume, 3 to 4 billion barrels of CO2, a giant or a supergiant CO2 field for every coal-fired power plant. That becomes big. Last part is the effectiveness. It has to stay down there a long time. I'm going to talk about that explicitly in a little bit after I give you a sense of what we're actually doing in the world today around this topic. Before you can inject the CO2, though, you have to separate it out from your flue streams. So a coal-fired power plant, the CO2 is about 12 to 20% concentration in the flue gas. For a natural gas plant, it's about 4 to 7%. You have to concentrate that, because otherwise you're just compressing a bunch of nitrogen. And you take up that pore volume with nitrogen, and that's kind of silly. So there's lots of different ways you can do that. Physical sorbents, chemical sorbents. You can also burn your fuel in pure oxygen. C plus O2 equals CO2. Do it that way. And there's lots of ways that that can be done. Cost is somewhere on the order of 40, 50, 60 bucks a ton. Okay? What that would turn into is about a 25% increase in your base electricity costs. So is it free? No. Is it a lot of money? Yeah, one could argue that. But compared to the alternatives, that looks pretty good. So we keep this one on the table. We pretty much understand how to do this. These are mostly pretty old technologies. We've been doing this for some level or another for 70 to 80 years. So that's not the issue. So the cost is in this part, but the trickiness is in the storage part and putting it underground. The thing that most people, again, don't know is we've actually been doing this for a while. The red stars here are places where we've been doing this at about 1 million tons a year for a while. And I'm going to talk about this one at Sleipnir. We've been doing it there for 11 years. But we've been taking 1 million tons of CO2 and storing it and monitoring it to make sure it does what it's supposed to do. Now, the green stars are places where we've been doing this for enhanced oil recovery. We inject CO2 underground and we get more oil out. We've been doing that for about 35 years in this country, and we've got about 80 projects that do it. So we've got a lot of knowledge about this. In total, we've put about 300 million tons of carbon dioxide underground through enhanced oil recovery. The yellow stars are places where people have spent a lot of money and stuff's going to happen very soon. One of these stars, the yellow one here, Snovit, is a project that came online yesterday. So that's pretty recent. This one's going to be the biggest, Gorgon. That's going to come online in 1.5 years. That'll be about 8 million tons of CO2 a year. Something like that. So a lot. About the same as one coal-fired power plant. So we've got some big projects and we've learned some stuff, but these don't give us all the answers we'd like. There just hasn't been enough science done there. And a big effort of the community now is to do that science to answer the questions that people need. So this is that Sleipnir Project. And they've been taking the CO2 from a natural gas field down here. They separate it on their platform and they inject it into one of these saline units. The reason they're doing this is because the government will cream them if they don't. Since 1996, they said if you vent it into the atmosphere, it costs you $50 a ton. And so they said, well, it only costs us $15 a ton to separate it, so let's do that instead. And that's what they've been doing. And they've put about 10, 11 million tons of carbon dioxide underground at this place. Now, this has been monitored. They use a technology that's sort of like ultrasound, where they're sending vibrations into the subsurface and tracking that. And we've been able to demonstrate that the CO2 has not leaked out over those 11 years. So that's good news. Part of the reason this technology is so important is because even if we pass laws like Norway's in the United States, if President Obama or President Clinton or President McCain came forward and said, I'm going to pass a $50 carbon tax, turns out that we still don't make laws in China or India. And again, most people don't quite get how big a deal that is. Last year, China put in 100 1,000 megawatt power plants. They put in 100 gigawatts of coal-fired power just last year. That's equal to about 1/4 of all the US's coal plants. They're going to do it again next year. They're going to do it again the year after that. That's a lot of CO2. That's why we're way above the worst case scenario. And India's not far behind, and they're gearing up fast too. And we, in India only, 40% of the people in India don't have electricity at all. Rural electrification is a major deal for them. They need it. What have they got as their resource? Coal. They've got the 4th largest coal reserves in the world. They're going to do this. And you want them to do it because it helps their people, but we have to manage the carbon dioxide. It's not something we can just stop thinking about. So the reasonable question to ask is, what if it leaks? I put the CO2 down. How do I know it's not going to come up? If it does, what happens? Is that something I need to be worried about? Good questions to ask. So I'm going to take a moment and do a quick demonstration. I'm going to leak some CO2 from you here. Okay? We've got some CO2 under here. Everybody ready? Go get the set up to go. There it is. That's right, it's dry ice. Dry ice is made of CO2. And it's leaking here. It's going into the atmosphere. Actually, I was cheating. All of us are already CO2 leaks. Right? Our bodies make CO2 when we breathe, because we're combustion engines. We take food, we burn it, and turn it into energy. But this leakage rate here, the leakage rate from this dry ice, is about the same as if you had a really leaky fault, and that fault were leaking CO2 rapidly. It would look kind of like this. It'd be on the order of grams per day is the leakage rate. It's small fluxes. And it's important to know this because people think about leaks of bad stuff, and they worry about it. Leaks of bad stuff are bad. You don't want, hazardous waste or, bromoform or plutonium to leak. These are bad things. But CO2 isn't really like that. CO2 is not flammable. In fact, the opposite. We put out fires with CO2. So it's a different kind of thing. And thinking about CO2 leaks, it's important to think about just like with climate emission, what do you care about? What do you want to avoid? And that's an important conversation to have. So let's go back to the computer here and see what we mean by that. You don't want the CO2 to leak. There's a bunch of reasons why. One, if it gets to really high concentrations, it'll kill you. It's an asphyxiant, and you want to avoid that. If it goes into the groundwater, it'll make Perrier if you're lucky, and then it'll be a punchline. But if it makes Perrier that has arsenic or cadmium in it, it will be a headline. You don't want that. Drinking water is important. You want to make sure the CO2 doesn't cause problems with that. Also, if you're being paid to put it underground, or if you're being taxed to not put it underground, you want to make sure that it does what it's supposed to do. You want your money's worth. So we know that these are issues. How do we handle it? The first thing is to make sure that a lot can't come out quickly. In this context, you care only about a handful of things, and they're all wells. Wells are places where you drill a hole in the crust so that you can get fluids to the surface quickly. That's a place where you could leak CO2. So wells are places where you need to focus and do some studying. The good news, though, is we actually know how to drill wells. We know how to remediate wells. We know how to recomplete wells. So that's okay. And this is actually a picture of a leaking CO2 well. This is a CO2 geyser in Utah. These guys were looking for oil and gas that hit CO2, and it's been erupting ever since. This has been since 1936. It's been leaking CO2. So this is water that's basically Perrier. It's full of CO2. And these guys aren't that worried about it. They're having fun. And Livermore went out and we measured that. It's about 50 tons a day is what comes out of that well. And on some level, again, that's a lot. If we had 50 tons of CO2 in this room, people would be worried about it. But 50 tons a day is also, if we had a 6 million ton a year injection, that's a fraction of a percent that would actually be leaking out of this well if you didn't notice this for a year. And you probably would, at which point you'd plug it and recomplete it. And we have a lot of experience from oil and gas exploration that lets us know that this is something we can do and do well. Ultimately, there's aspects of this, though, that we don't have a lot of clear ideas on. We do suspect that the risks get bigger while you're injecting, and then when you stop injecting, the risks go down. And this is work from Sally Benson, who's at Stanford now. And she basically said, look, the pressure builds up, and when you stop injecting, the pressure drops off, and that's the major element of the risk, and that's basically the case. Now, we don't actually know the shape of that curve, though. It could look like this, right? But it's basically going to have the same form. The risk is going to go up until you stop injecting, and then it's going to go down. That said, there's things we'd want to know about this better. In order to do that, we need large injection projects that we can study in detail and learn, where we can validate the simulations and models that we have, where we can capture samples of the rocks and run experiments and make sure the CO2 is doing what it's supposed to do. We don't have anywhere near enough of these projects. That Sleipnir project that I was talking about is this one here. That's about a third of what a 500 megawatt power plant puts out. The biggest single injection we have anywhere is this one here, the Altura field in Texas. That is about the same volume as one coal-fired power plant, 1,000 megawatt coal-fired power plant. We need dozens of these things. We need hundreds of these things to really make sure that this is a technology that works well. Because in order to get that one wedge of abatement, we need 800 plants that look like that. And if we don't have that much, we're not going to do much. Thankfully, there are people on the job. Many academic institutions, many government institutions, many of the national labs, including Livermore, have substantial research efforts in this. And money is finally being spent on this problem. And we're tackling three aspects of this that matter. One is carbon capture. We've got to get the cost cheaper, because that'll make it easier to deploy this technology. And so we're working on different things: membranes, novel fuel cell designs, trying to combine capture processes with things like desalination to make it cheaper and to make it work. We are working also on the sequestration end of things. We've got advanced simulators. So if we want to know what happens in 50 years, in 500 years, in 5,000 years, we have some way to think and talk about those. If we're going to put the CO2 down, we need to monitor it over time. And so we've developed monitoring technologies. We have special ways to integrate those monitoring tools so that if somebody says, what's the cheapest I can do this for, that still serves the public interest, so we can answer that problem well. We want to avoid these risks and hazards. So we need to calculate the chance that something can go wrong and what happens if it does. We need to identify things that are wrong at a site, or potentially wrong, and figure out how to avoid problems associated with those hazards. And the last thing is, how do you actually characterize a site? What's minimum level of due diligence? What does an operator need to know to make sure that they choose a good site? Because we talk to operators, we're working with industry, and they want to know desperately how to do this. But there's no cookbook out there where they can sort of go out and say, well, yes, I need a soupçon of cap rock. They need to sort of figure this out in a way that matters to them. And that information is not yet available. Good research program. The last thing, we're not going to walk away from fossil fuels anytime soon. They're too good, they're too cheap, they're too abundant, they're too well distributed. So we should be thinking about better ways to use them. How can we get them out of the subsurface by drilling fewer holes? How can we reduce the environmental impacts associated with them? There are new ways to convert them so that we get away from needing to do this at all. And those are interesting and important questions which we are increasingly focused on. We've talked about climate change. We've talked about the CO2 increases in the atmosphere and why that's an issue. We know that it comes from the burning of fossil fuels. 85% of the problem is from that. We also know that out of the many options we have in front of us, efficiency, wind, nuclear, solar, biofuels, all of these great options, sequestration is one, and it's a good one, and it's an important one that we want to keep on the table. And finally, that we're trying to do something about it right here, and working closely with industry, working closely with government and regulators to try to get this to a position where it can be deployed quickly and safely and well in the world. That ends my presentation. Thank you very, very much for being here. I'm just delighted to have you. If